All right, let's run through some review problems here on the unit. So they give you an equation g of x. They show you the graph. It is a quadratic. It's a parabola on the graph. Find g prime of -4 and explain what this value represents. So we have g of x. We're going to rewrite it. So I need to multiply or square the x plus 2. Then I need to multiply the 1/2 into that. And then I get plus 2 minus 4, so it becomes -2. So then the derivative, so the derivative is x plus 2, so g prime of -4 is -4 plus 2, so we get -2. If I look on the graph, that means at the x value -4, if I were to draw the tangent line, with a ruler, at the point of tangency, the slope of that line would be -2. So we'll say that g, we'll write that out, prime of -4 equals -2. Second one, find the equation of this tangent line and sketch a graph of the tangent line on the grid. So I already sketched the graph, but let's find the equation of the tangent line. So first I need the point of tangency. And so that's going to be at -4, and then I got to plug the -4 in. So we're going to say that g of -4 is -2. So if I write that as a point, -4, -2 is my point of tangency. Now we need the slope of the tangent line. We found that before. We found out that g prime of -4 is -2, so we knew that. So that means the slope of our tangent line is -2. We need those two highlighted pieces of information to write the equation of the tangent line. Using the equation of the tangent line, find the value of y when x equals -3.9. Then find the value of g. Okay, so we're basically doing an approximation here. So at what value? At -3.9. So if we're approximating, if I zoom in as far as I can, we're going to actually find the point -3.9 something on the tangent line as an approximation for -3.9 on the curve. So plugging it into the curve. So they want us to kind of do both. And we can see because the graph is concave upward, our tangent line will be below the graph, and that will make it an under approximation. So that's kind of what they want us doing here. I'm going to talk a little bit more about what that is. So you can see that what we can do is we can use the tangent line as an approximation for the curve. That's one of our first applications we're going to use it for. So I think it's important to take a look at that on Desmos. So if we look at this in Desmos, we have our curve here and then the tangent line, the equation that we came up with. So I have both graphed. You can see that they're tangent at -4,2. What we're going to do is if we zoom in, if I zoom in on the x value, -3.9, remember the blue one was the curve and the orange one is the tangent line. We can plug -3.9 into the tangent line, get the y value, and use that as an estimate for if we plug -3.9 into the curve. Why would we even want to do that? Well, not necessarily for this equation, but in the future, plugging an x value into a crazy equation with lots of arithmetic to do, maybe you're raising something to the 5th power and there's division and the whole thing. Sometimes it's just easier to plug it into the equation of the tangent line because that equation will always be simple. It's always the equation of a line. You multiply it by the slope, you subtract the intercept, and you have your y value. And you can see that it'll be a good approximation. So you can see that the curve is above, so our approximation here is too low. I'm gonna ask you to explain that quite often. And the explanation is you have to talk about the concavity of the graph. Which way the graph is opening, that's concave. So this graph, if I turn off the tangent line for a second, and I'll turn off my approximations, this graph is concave upward, meaning it opens upward. So anywhere that I draw a tangent line, anywhere on this graph, the tangent line will be below the curve, which you can see is the case here. Okay, and that's because the graph is concave upward. If the graph opened downward, like think of this parabola was flipped the other way, when I draw a tangent line, the tangent line would be on top of the curve and your approximation would be too high. So again, as we zoom into our approximations, right, you can see the orange one's below, which is the tangent line, below the blue one. So that's how we know it's going to be too small. Now, we even have the values here. It tells me that when I plug it into the function, I get -2.195. And when I plug it into the tangent line, I get -2.2. Well, -2.2 is below or too low of an estimate because it's a bigger negative number, and that's too small. Right? So that's what they're going to be asking us. Hopefully Notability didn't crash. There we go. All right, so there's the equation of our tangent line. So what they're saying here is using that equation, find the value of y when x is -3.9. So typically when we're going to plug into this tangent line, we're going to want to solve it for y. So I get, if I distribute the -2, I get -8, and then I'm subtracting 2, I'm going to get -10. So if I plug in -3.9, I'll get a y value of -2.2, which is what we saw on Desmos. Okay, so it said using the equation of the tangent line, find the value of y. So we did that. They're not talking yet about it being an approximation. We're just sort of getting introduced to that. Then find the value of g. So now they want us to plug it into the function and see what we get. So when we plug it into the function, we get that number. Okay, so we can see that our approximation is below that number. It's lower than it. So what do you notice about the values of these two results from question number 3? What does this imply about how the equation of the tangent line might be used? So we're going to say that the y values are really close. Let me write this out. The y value of the tangent line and the y value of the function at x equals -3.9 are very close. So we can say now that our tangent line, we can use to approximate function values for at x. So here's the key: function values at x values very close to the point of tangency. Again, why would we even want to do this? Thinking about calculating these two y values, which one's going to always be easier for the most part? I mean, it's going to be the plugging into the equation of a line. This will always be the equation of a line because we're talking about a tangent line, right? So it's always going to be the same amount of work. This is just we're at the mercy of whatever the function is. This function's not horrible to calculate, but we might have one that's a little crazier to calculate, right? And the key here is that it's only a good approximation when your x value is close to your x value for your point of tangency. So this point of tangency, I want to turn those off for a sec. Our point of tangency was -4, and look at, we were evaluating x values at -3.9, really close to that. Of course, the approximation stinks if I try to use that tangent line to approximate, say, f of 0, right? I would get, let me see both at the same time. If I plug 0 into the function, I would get -2. If I plug 0 into the tangent line, I get -10. Those are not close enough. Those are very far apart, and that's because my x value is not close to my point of tangency. If I stay right around the point of tangency, this is a concept called linearization. When you really zoom in really close to a curve and its tangent line, you can barely tell the difference between the two because any curve will flatten out and get really close to the tangent line. It will look linear. Any curve ends up looking like a line if you zoom in close enough. Even if I were to look at a really curvy part down here at the bottom, if I zoom in close enough, it becomes linear looking. So that's why this thing works, okay? But it only works if you're zoomed in really far, meaning your x values that you're trying to approximate for are very close to the point of tangency. That's the only way it works. All right, so we're going to use that idea as we go through this. That's sort of a new thing. All right, picture at the right is the graph of the function g. That's a square root function. Use the graph and the equations to answer the following questions. All right, so based on this graph, at what values does the graph of g have a horizontal tangent line? Looks to me like there's probably a horizontal tangent line right there at an x value of 1. So it looks like g of x has a horizontal tangent line at x equals 1. Give a reason, because I just drew it in. I could say, show the algebraic analysis, but I drew it in. How do I know I'm going to have horizontal tangent lines when I draw them in? Typically, I'll say because g of x has a relative maximum. Now we want to show that that is actually the case. So if I take the derivative, I should be able to show there's a horizontal tangent line there. So I'm going to rewrite g of x. So then g prime of x becomes x to the -1/2 minus 1, which is 1 over the square root of x minus 1. So if I want a horizontal tangent line, I can set my derivative equal to 0 and solve for x. So I get 1 equals 1 over root x. If I cross multiply, I get root x equals 1. So then x has to be 1. That verifies what I just saw. So we can say since g prime of 1 equals 0, So the derivative at 1 equals 0, then g of x has a horizontal, oh, pen just died. Let's pause it here while I charge up. So then g of x has a horizontal tangent line at x equals 1. On what intervals is g prime of x less than 0? Give a reason for your answer. Remember, less than 0 means negative. So for what intervals is g prime of x negative? We're going to say that g prime of x is negative. Or I'll say, I'll use their notation. So you get used to it. G prime of x is less than 0 on the interval (1 to infinity), because g of x is decreasing. So if we look at g of x, our equation here, if we look at the graph, remember that anywhere g is going down, which looks like from here on forever, that g prime would be negative. Right? Anywhere the rate of change is negative, g is decreasing, or vice versa. On what intervals is g prime of x bigger than 0 or positive? Remember, that means positive. So it's going to be the opposite thing. G prime of x is bigger than 0 on the interval wherever it's increasing. So it's increasing from 0 to 1. So my reasoning is that on the graph, I see that g is increasing, so g prime must be positive for that interval. For what values of x is the slope of the tangent line equal to 2? Show your work. So for this one, we want to know when is the derivative equal to 2. So I know g prime of x is 1 over root x minus 1. Set that equal to 2 and solve. So I add 1. So I get 3. So then I got 1, I'll just draw my arrow, 1 equals 3 root x. Whoops, put a root 3 in there. So then I'm going to divide both sides by 3. So root x equals 1/3. So that means that x is going to be equal to 1/9. That would be the x value for which the slope of the tangent line is 2. So if I looked on this graph, x equals 1/9. That's pretty early on in the graph. If I drew the tangent line pretty early on, that makes sense. It looks like it'll be about right. Again, it's not a very accurate drawing, but I just wanted to give you the idea of what it looks like. Find an equation of the tangent line drawn to the graph of g of x when x equals 4. Then draw the tangent line on the grid above. All right, so if I want the equation of the tangent line, first I need the point of tangency, and then I need the slope of the tangent line. So that's going to be at 4. We want to know, so we have to find, oh, not f, it's g. We want to find g of 4. We need to find that y value. So g of 4 is going to be equal to 2 times root 4 minus 4 plus 2 equals, that comes out to be 2. So that means 4, 2 is our point of tangency. Now we need the slope of the tangent line. And the slope of the tangent line will come from, g prime of 4. We found our derivative to be 1 over root x, so it's going to be 1 over root 4 minus 1. So that works out to be 1/2 minus 1, negative 1/2. So that's the slope of our tangent line. So now they want us to write the equation. It's y minus 2 equals negative 1/2 x minus 4. All right, now we're going to do some stuff based on a table instead of the graph. So the table below, we have to figure out, does it represent h or h prime? The table below represents values in the graph of the derivative. So now we're going to have some values of the derivative, and they're going to ask us stuff about the derivative, but also about the function itself, the h. There's a couple other things that we want to assume here, or that we have to assume. So they're going to ask us on the first one, what intervals is the function? Oh, we got a phone call coming in. We decline that. On what intervals is the function h of x increasing and decreasing? Give reasons for your answer. So remember, they're telling us values of h prime, but they are asking about h. When they're talking about intervals of x, we're going to answer with these numbers up here on the top. So on what intervals is the function increasing and decreasing? So first of all, we note that it looks like we've got our positive. Let's identify our positive derivative values. It also says that those are the only zeros. So the zeros are the spot where you might have a relative maximum or minimum on h. Those are the zeros of the derivatives. And anywhere where the derivatives look to be positive, whoops, these are negative. Anywhere where the derivative looks to be positive, that means h would have been increasing. So we could say h of x is increasing on the interval negative infinity to negative 2 because the derivatives there are all positive or bigger than 0. Remember, we know this is a polynomial function, so there's nothing kind of weird happening here where I have to worry about the sign switching. If those couple are positive, then all those y values are positive, and it starts from negative infinity and goes up to negative 2. So I know where h of x is increasing. H of x, I also know where it's decreasing. It's going to be decreasing. H of x will be decreasing anywhere that h prime of x is negative. So that would be on this interval, it's negative. So that's going to be from, negative 2 to 7. And then it happens again. These are all negative from 7 to infinity. Right, from 7 to infinity it happens. Erase all this stuff. So we're also going to say from 7 to infinity, because that's where the derivative is negative. Next up, at what x values does the graph of h have a relative minimum? Justify your, relative maximum. Justify your answer. So we're going to say that h of x has a relative maximum at x equals negative 2. I can't find the y value for this, by the way, because they don't tell me what h is, so I can only tell you the x value at which this occurs. Has a relative maximum at x equals negative 2 because h prime of x changes from positive to negative. So right here is where they switch from positive to negative, the derivatives switch. So that means there must be a maximum. At what x values does it have a relative minimum? We're going to say that h of x never, because if I look at the table, it never switches from negative back to positive. So h of x never has a relative minimum. Because h prime of x never switches or changes from negative to positive. Okay, if h of 3 equals 2, what is the equation of the tangent line to the graph at x equals 3? What is the equation of the normal line? So, okay, if we want the I'm going to save a little bit of writing. You shouldn't abbreviate with point of tangency like that. You should write it out. But I'm going to save a little bit of space here. So the point of tangency of the tangent line is 3, 2. The slope of the tangent line, again, I'll just abbreviate here, is going to be h prime of 3, which on our table is -3. So that's the slope of our tangent line. So the equation of our tangent line will be y minus 2 equals -3 times x minus 3. That's the equation of the tangent line. Now at that same point of tangency, they also want the equation of the normal line. So they're not really saying anything about explaining, so I'm just going to jump right in and say that the slope of the normal line is going to be 1/3. I don't have to explain that. I don't have to write it out. We know that they're perpendicular, so their slopes are the opposite reciprocals of each other. So I have 1/3, so then it's the same point of tangency, so it's going to be y minus 2. In this case, it's not tangent, but y minus 2 equals 1/3 x minus 3. That's going to be the equation of the normal line. Okay, 14, find the tangent line approximation of h of 3.1. So above, we just found the tangent line at an x value of 3. So now we're really close to that x value of 3 at 3.1, so we can use the equation of our tangent line to approximate. So when we want to use the tangent line to approximate, we do want to solve for y. It's a little bit easier. So I just took my tangent line, solved it for y, and now I'm going to plug 3.1 in for x and solve for y. So it's going to be 1.7. So what I could say is if I plugged 3.1 into h, I would get about 1.7. So instead of y over here, maybe I write this. I write h of 3.1. Even though I'm not plugging it into h, I'm plugging it into my tangent line. I can write that if I write is approximately. So actually, I shouldn't write it here because I didn't plug in the 3.1 yet. Sorry. So there's my approximation. Is this approximation greater or less than the actual value of h of 3.1? Well, this was now, remember, the tangent line was drawn at x equals 3. And I have to know which way the curve is opening, or what's the concavity of the curve at 3. So I can tell that because they told me, they said the function h is concave upward when x is equals to 3. So the reason they tell me that is at 3, wherever I drew this tangent line, if the graph is concave upward, when I draw a tangent line at 3, it's going to be underneath, even if the function was sort of going up at that point, right? The tangent line's still underneath. So if the tangent line is underneath the curve, that means this is an under approximation. So this approximation is less than the actual value of h of 3.1 because the tangent line is under the function h of x. All right, so there's that guy, and there's my explanation. Now they want us to find the value of each limit, each of the final limits of h of x. As x approaches negative infinity, so I'm going to go back to the table, and as x approaches negative infinity, it looks like what's happening here. These values are going 5, 11, they're getting greater, it looks like. So the limit seems to be going up unbounded. So we'll say it's infinity. And then as x approaches infinity, so on the right side, it seems, oh wait, I'm sorry. This is h prime of x. And they're asking about the limit of h of x. So what has to happen here is when we're looking at h prime of x, the value of the derivative seems to be getting larger and larger as I move further and further left. Now, they're positive, so that's the key here. Since the derivatives are positive, I know the function's increasing from left to right. So if you think of the function increasing from left to right, that means the limit as x approaches negative infinity is going to be negative infinity because it's increasing. So it would have been started down at negative infinity. That one was a little tricky to think about. I started looking at the table as h. You got to remember that you're looking at h prime. Now, on the other side, as x approaches infinity, h prime is negative and it's becoming a bigger and bigger negative, which means if h prime is negative, the function's decreasing, and it just keeps decreasing and decreasing the further out you move for x. So that one's also going to be approaching negative infinity. So that's how you can interpret those values. Okay, here we're given not the table, not a graph, but an equation of a derivative. And they're going to ask us about f. So on what intervals is f of x increasing? So what we want to do is we want to do a sign analysis. And this, just thinking about, sign analysis on f prime of x. And thinking about your last unit's quizzes and tests, this would be similar to the properties of limits. I took my time to kind of go through and make sure I write out all the properties on the homework, on the answer keys, and very few of you showed me answers on quizzes or tests using the properties when I asked you to show me the properties. This is a similar thing. Like, you might be able to blow through this without doing the sign analysis on f prime. But on a quiz or test, it's going to say, you know, show your sign analysis. This is what I'm talking about. You need to be able to do this. So you need to show this number line for f prime of x. So what makes, the first thing is I put my zeros on the number line. So I'm trying to figure out for what x's do I get a derivative of 0. So since it's already factored, that's kind of nice. I know that when x equals 0, when 2 minus x equals 0, and when x plus 3 equals 0, that's when my derivatives are going to be 0. And I put those on this line, on this test interval. I'm testing the sign of the first derivative. So it looks like it's going to be at 0, 2, and negative 3. So I'm going to say that I'll space them out like this. Negative 3, 0, and 2. And I like to say, I put a little dividers because I'm going to be writing information. I like to say the derivative at negative 3 is 0, the derivative at 0 is 0, and the derivative at 2 is 0. So now what I want to do is, I know that since this is a polynomial, I know that all the x values on this first interval from negative infinity to negative 3, they're all going to have the same sign. That's why I'm calling this a sign analysis. The derivative, the sign of the derivatives will all be the same. They only switch, or possibly switch, when the derivative is 0, which I found those 3 spots where they could possibly switch. So all of these stick together. So I'm going to pick any number on this interval, like say negative 5. And I'm going to plug it into the derivative, and it's in factored form. So if I plug a negative 5 in, this first guy becomes negative over here, right? I'm looking at my derivative. The second one becomes a positive, and that third factor becomes negative if I plug in a negative 5 into those. So a negative times a positive times a negative, that's going to be a positive. So I know that the derivative at negative 5 is positive. That tells me a lot about f. It'll tell me when f is increasing, when f is decreasing, which is what I'm looking for. Now, what number will I pick on this interval? I'll choose negative 1. If I plug it into my derivative, I'm getting a negative times a positive times a positive. So I'm getting f prime of negative 1 is negative. I'm going to do the same thing on this interval. I'll choose x equals 1. So I'm going to get f prime of 1 is going to be positive. Because I've got a positive times a positive times a positive. And then on this interval, from 2 to infinity, I'll choose like x equals 5. So I know that f prime of 5 will turn out to be negative. So I've got a positive times a negative times a positive. So let me shorten this up a little bit because I need room to write. Whoops. Okay, so I want to answer the question now based on this sign analysis. When is it increasing? When is it decreasing? So I'm going to say f of x is increasing on the interval, I should say on negative infinity to negative 3 union 0 to 2 because f prime of x is bigger than 0 on those intervals. So I'm looking for those positive intervals. So from negative infinity to negative 3 and again from 0 to 2. The same will be true for decreasing. So it's going to be decreasing on negative 3 to 0, union 2 to infinity, because on those intervals the derivative is negative. So remember, less than 0 means negative, bigger than 0 means positive. At what values of x does the graph have a relative minimum? So I will say f of x has a relative minimum at x equals 0 because the derivative changes from negative to positive. What value does it have a relative maximum? So f of x has a relative maximum at x equals negative 3 and x equals 2 because f prime of x, the derivative, changes from positive to negative. So let's look at that. So I'll grab a different color. At negative 3, x equals negative 3, our derivative changed from positive to negative. So a positive derivative meant f was going up, and then a negative derivative on the other side means it was going down. So the f was going up, and then it turned around and started going down. That means you must have a maximum there, right? If the function's going up, turns and starts going down, that means there's a relative maximum there. So that's how we figure that out. And the same is true for a minimum, vice versa. So I'm looking for where it switches from negative to positive. So there's 2 spots where it switches positive to negative, 1 spot where the derivative switches from negative to positive. Now they're going to give us some more information about f here, some information, have us draw the equation of the tangent line. So first I know the point of tangency is going to be 4, negative 1 because of that information. The slope of the tangent line will be whatever f prime of 4 is. So we have to plug 4 into our equation here. Our equation is f prime. So if I plug 4 into that, you guys can work that out. I've already kind of worked out the answer. We get negative 56. So they want the equation of the tangent line at x equals 4. So we have our point and our slope. So there is our equation of our tangent line. All right, approximate the value of f of 4.1. So again, we just came up with the equation at 4. So now they're going to pick a point really close to 4.1 and want an approximation. So we can just plug our 4.1 into our tangent line. Now, we can't even plug it into f. Like, you know, I said we do that because it's easier. In this case, we can't plug it into f because we don't even have f. We have f prime. So the only thing we can do is approximate, and we can understand if our approximation is too high or too low. So to approximate the value, first I'm going to solve my tangent line equation for y. So it's going to be negative 56x plus 223. So now to approximate 4.1, I'm going to say is approximately what I get when I plug that in to my tangent line. So that's going to be about negative 6.6. And so we want to say that is it a over approximation or an under approximation? That's going to depend on the concavity of the original graph f at our point of tangency. It says f is concave down. So whatever we're at 4, the graph is concave down here. So that means if I draw my tangent line, it's going to be above. Whether the function's decreasing or not, maybe it can still be concave downward and increasing. Maybe the function's like that, right? Either way, though, you can see the tangent line sits on top of the curve when the curve is concave downward, which means our approximation is going to be an over approximation. So we'll say since f of x is concave, I'm going to clear myself some room here, up the tangent line I'm sorry, it's concave down. What am I saying? Since it is concave down, the tangent line is above f of x at x equals 4.1. Thus, the approximation is an over approximation of f of 4.1. Okay, let's move on. Last one here. Pictured to the right is a graph of the derivative of a polynomial function. Use the graph to answer the questions. So they're giving us a graph of the derivative, and they're going to ask us about p of x. On what intervals is the graph of p of x decreasing? So I'm going to restate p of x is decreasing when, or I'll give the interval first, is decreasing on the interval -3 to 0 union 0 to 3, because the derivative is less than 0. So how do we want a graph of the derivative when it's less than 0? Anywhere where it's below the x-axis. So that's all of those spots. It's below the x-axis from -3 to 0, and then again from 0 to 3. I should use opens, right? From there to there, and then again. Right? It's not below right at that one spot at 0. It's actually back to 0, so I can't say it's negative. So that's why I have to break that up. Same is true for the next question. We're talking about increasing. So we're going to say p of x is increasing on the interval -∞ to -3 union 3 to infinity, because p prime of x is bigger than 0. All right, now they're going to ask us about a maximum and a minimum. So at what value does p of x reach a maximum? So there's a relative maximum on p when p prime switches from positive to negative, which looks like that occurs right here from above to below. Does it ever happen again? No, that's the only spot, it looks like. So we're going to say that p of x reaches a relative maximum when, or I'll say add again, I like saying that first. So the restate and then answer at x equals -3. I can't find the y value because I don't have p of x. I don't have the original function. But I could say the x value for which it occurs, because p prime of x changes from positive to negative at that x value. So then vice versa for the relative minimum. So we can say p of x. You can try this on your own. Pause the video, see if you get the right answer.